All right. Hello, everybody. I'm Lizzie. I'm one of the Student Learning Hub coordinators at C2 Smarter. And welcome to today's online hub, which is an education and workforce development initiative that offers applied learning and skill building opportunities to help you develop research and job ready knowledge. Today's course is Where Are All the Robots and Why Aren't There More of Them? Well, an omnipresent element in almost all sci-fi content, robots remain hard to find in our daily lives. When's the last time that you have seen a functioning robot doing useful work in our society? However, despite the limited public exposure, robotic technologies are undergoing rapid improvements in their own corner. Today, our presenter will speak about some of the latest advancements made in academia and how we are just starting to see robots maturing into useful products. You will also discuss some of the biggest hurdles going forward and conclude with a case study on Amazon Robotics' rocky adoption of robotics technologies. And today's instructor is NYU's Irving Fang. Irving is a second-year computer science PhD student at NYU's AI Force Lab, researching robot manipulation. And he obtained his undergraduate degrees in data science and pure mathematics from UC Berkeley. He has published several first author papers at top robotics and computer vision conferences, such as RSS, ICRA, CVPR, and more. So with that, I will hand it over to him to get started.
All right. Thank you so much for the nice introduction. So today we will be talking mostly about robotics, and it will be a high-level survey of the field with some slight technical details sprinkled in. And if you like robots, I hope you can enjoy this discussion. So a little bit like repeat of the introduction that Liz just did. So I'm a second-year PhD student at NYU. I did my undergrad in math and data science from UC Berkeley, which is like all the way across the country. And I research robotics, specifically that has contact reach interaction with the world. For example, robots that handle stuff in its hand or like uh, need to push something or even interacting with humans with close contact. I used to work at Mitsubishi Electric and also a startup company from Berkeley called Squishy Robotics. So the overview of today's talk is going to be these 4 points. Basically, what is robotics and what have we done with robotics in the last few decades? And what are some of the hurdles going forward? And some simple case study on Amazon Robotics. So I want to open our discussion with a video from decades ago. This is Honda's humanoid robot called Asimov. So as we can see in this video, there is a robot that is shorter, like a little human walking around and carrying a backpack and walking very slowly and trying to. And the presentation, the idea of the presentation is to let the robot walk on the stair. And while the title already kind of spoiled it, but later on we'll find that this robot failed to do so. Uh, like he basically falls down the stairs. And for anyone that is very interested in robots, maybe as a kid, the Honda Asimov is a very famous, like a world famous robot that made into the public eyes. And traditionally, when we talk about robots, we also talk about these type of machine humans that has a little sci-fi elements in it. But I'm gonna show you that like there are actually a lot more type of robots, or people call them robots. So on the left, we have this type of industrial robot, where it shapes like a human arm, and on the right, they are very strong. They can carry like component of car or other industrial components that are very heavy, and they also can repeat a same action like over and over with very high precision, make them very ideal for very repetitive tasks. And on the right, we have this intuitive Da Vinci medical robots. They are very precise, and they can cut a very little incision to the patient's body and can perform surgery that are actually not possible at all with human surgeon. So in this video, I briefly can show you a Fang robot factory in Hungary assembly Audi car. And as we can see, this robot can carry this like very heavy metal component with relatively ease and can piece things together with very high precision. By the way, during this presentation, if you have any question, please don't feel hesitant to interrupt me and just ask the question. So, and this is doing some tracing some certain line with very high precision. And on the right, we have this medical robot from Sony, yeah, the company that make the PlayStation. They are showcasing a robot doing a mock surgery on a corn kernel. So they're trying to mimic stitching a wound on the human body. And as we can see later, it basically perform a very precise manipulation on this corn. And these are just two type of robot. And in the wild, we also have these kind of robot dog that has like 4 legs. Similar, that's where they get their name from. And also we have these type of autonomous mobile robot that we often see in factory or warehouse where they can carry very heavy payload and walk around. So one question like arises like, isn't the quadruped like the on the left also a sort of a mobile robots, right? Like why isn't it called autonomous mobile robots? And as we can see, like these names and classification are just mostly marketing jargons and human construction. Uh, they are not uh, they're not like the essence of the robot itself. So this leads to the following two type of robot, that is drones, like unmanned aerial vehicle, and also the autonomous vehicle. So this one is a newly unveiled Tesla autonomous cars, the concept art of them at least. So they use very similar underlying technology with all the previous robot that I showed you. So this again brings a even further question. So what actually is a robot? Like, is Amazon's Go cashless grocery store also a robot? So this is type of store Amazon uh, doing experiment on where there's no cashier. You just go in and scan your Amazon account and you grab everything you need and just go out. There will be sensor up like in the on the roof, like sensing what items are grabbed. Based on your phone, your location, you can calculate what item you actually took away, and automatically deduct some money out of your Amazon account. So basically, it follows a like replacing human labor pattern. Like it sends and plan, think about a little bit, and then act by deducting money. So AI power. So is this thing also a robot? Like this is a little bit hard to say. So robot, but what we can conclude from this little presentation, little series of robots showcase is that robots are not necessarily humanoid, but they do tend to be usually bio-inspired. For example, this robot dog is obviously inspired by uh, mammals with 4 legs, and these robot arm are obviously, and this medical robot arm, they are obviously bio-inspired by humans' features such as our arms and hand. So generally speaking, we do tend to study those machines that are bio-inspired. But without a very ironclad, a very strict definition of what is robots, we usually study stuff that's humanoid, so shaped like a human, robot arm, quadruped, like mobile robot that with wheels, drones, and autonomous vehicle. So, like if you present a research that study on these cashierless grocery store, we usually wouldn't consider a robotic study, even though some of the underlying technology is exactly the same. So after we talk about like what is robots, like what makes something robotics, I want to talk about some recent progress in the academia community, and some of them, and they're not necessarily in the order of like significance, although I do pick something that I do think are some of the biggest breakthrough in the community. So this is the same video of the Honda Asimov that I showed. It's debuted in 1996, so that is almost 3 decades ago. So this robot walks kind of awkwardly, and also later on failed a very simple task of climbing a stair. But on the right, we have this Atlas, a Boston Dynamics robot that can do all these very impressive tasks that even a healthy human sometimes struggle to do. So a natural question to pose is like, what enabled this significant breakthrough in just a span of 3 decades? So, but to answer this question, let's first take a little time travel and back to 2001. So that is 2 decades ago. There is a very interesting research coming out of Cornell's RENA lab. It's called passive dynamics walker. So let's look at this, like what it's actually doing. So this is a robot walking down a ramp without motor, without electricity, just a skeleton, like a metal shaft pieced together, and it can walk down the ramp like with a very natural gait and human-like behavior. So if we look at now looking back, like comparing these two things, right? Looking at these two, um, one of the major differences of the Asimov is that Asimov work in a very stiff and slow manner. It's like a astronaut. Like the back of the robot is always very straight and doesn't really look like a human at all. That doesn't look like a human on Earth, to be precise, I would say. Whereas this robot uses a lot of motors and electricity and energy, and there's a battery pack on the back. So why is that like such a sophisticatedly engineered machine performs so much worse than this very simple shaft pieced together with no electricity, no motors? The answer is that, without getting very technical, is that the answer is that we subconsciously utilize the natural dynamics of falling down to be able to do the walking behavior. So instead, the Asimov robots on the left use a very conservative control strategy that let the motor cancel out every possibility of falling down. So the robot worked very stiff because every motor is exerting very strong power to the uh, to the to the natural dynamics of this system. So the robot won't fall down, yes, but it also works very conservatively. Whereas uh, on the right, the robot is walking, utilizing this falling down dynamics. So there's a ramp, right? Like if you put a ball on this ramp, the ball will just like rolling down, rolling down. By the way, what is this? What is this yellow line on the screen? And there's this yellow line on, sorry. And this is like utilizing this dynamics instead of actively trying to cancel out this falling down dynamics. And this is a very key insight that give rise to the better bipedal locomotion that we see today. So this is another humanoid robots company called Agility. They're collaborating with Amazon. Uh, they can perform these manipulation, like moving like empty bins around. And The reason I brought up this company is because this company is founded by Professor Jonathan Hurst, and Jonathan Hurst is a robotist that has very like extended experience of using these kind of dynamics, this bipedal dynamics. So precisely because now we have a better understanding of this dynamics, how we can utilize this falling down tendency, that we are creating these better humanoid robots. In a sense, this is similar to how different birds and airplanes fly. A bird can use very little energy and it can stop on a tree like with ease, but our human aircraft, it needs an immense amount of energy compared to its body weight to be able to fly, and we will not be able to do any like tricky maneuver like stopping midair to land on the tree. But that are very easy for birds and any living creature to do, and precisely because they subconsciously they learn how to manipulate this natural dynamics of the body weight. So this similarly, this gives rise to better quadruped locomotion as well. And while I will omit some technical details here, but quadruped is like obviously a lot easier than bipedal, like two foot. So this is trying to showcase like some of the some of the capability of like evolving bipedal robots. And one thing I want to highlight is this behavior of walking upstairs. So this is one of the major reason we want to have legged robots instead of wheels or whatever other like locomotion techniques. So these wheels do provide a better like traversability when it comes to these difficult terrain. And uh, quadruped are like slightly easier, like I said, slightly easier to handle than bipedal, but under the hood, uh, the improvement we are seeing recently is also due to some of the reason I mentioned, that we now have a better understanding of this dynamic system, of this walking dynamics, that we were able to create these improved robot system. So another very recent progress that we are seeing is that traditionally most of the robots walk in a cage or no man condition. So for example, in this case, there's a there's a yellow cage around this KUKA robot doing whatever task. I'm not exactly sure. Seems like a demo. The reason is because these robots has very limited perception capability around the environment. They do not know what's going on around them. They just do whatever they're programmed. Um, and when the collision happen, when a robot collide with a human, the robot will not know, uh, will have very limited understanding of what it collide with, and it will basically keep going and crush the human bones. Like a human is very fragile in the face of a robot, a walking industrial robot. So, but this is changing uh, because now we have this so-called cobot, short for collaborative robots, and they can work alongside humans in limited capacity. This is a factory in China, Xiamen, where they are they're making, I believe, like car components. And I'm trying to find here, as you can see, we can see this humans walking with this robot in very close proximity. They are feeding this parts to this little. I'm not sure what this is, and the robot can pick the stuff immediately, and overall there's very little safety concern with this. Well, there are some like there are different regulation standard across the world. So in some place, this kind of factory laid out is not ideal. Maybe uh, will be illegal. But this also showcases that today there are industrial robots that are much safer to work with humans. unlike the one that I showed previously, where it has to be put in a cage. So this is a video not I took, but this is actually a robot in Muji in Hudson Yard, NYC, where it's doing a little bit of a barista work, doing coffee, making coffee, and handling relatively fragile items such as a plastic cup, and doing uh, and a lot of like the stuff that you need to eat, so they need to be they need to be safe and usually very soft. And now these cobalt can also handle these very dedicated objects. So what enable this transition? Like why we are having these robots now, and why are industrial robots so usually dangerous and only in confined environments? So there are a lot of reasons for this. So one is sensing. So the robot can now see better around the world. I will talk about this later in more details. But another thing is that now we have better control algorithm or another way to put it is that we always know there are certain control algorithm that can make robots safe when there's contact. But back in the day, we didn't get much adoptions, and we also didn't really apply them to robots. We apply them in other engineering domain. And this is an example of a compliant motion, exercising compliant motion. So meaning that the human can sort of play with this robot, and the robot will not be very stiff. It will sort of act like a spring that if you push it hard enough, the spring will compress. And if you push it relatively little force, the robot will not move, will not like react as hard. So this is enabled by some like additional sensor in the robot and also a clever algorithm that can enable you to do so. So this makes robot like relatively safe. As you can imagine, if there is a collision between the robot, the worker, and the robot, because when the collision is hard, the robot will become soft, will act soft, not be the material will not change, but will act more softly, resulting in less dangerous collision. And talking about talking about sensing and perception, this brings us to another very major, I would say, advancement that we have seen in the last few years. That is, like many autonomous system, or is that like many autonomous system, the robot generally follows a sense, plan, and act model. Basically means that the robot first sense, like maybe by seeing, like using a camera, maybe by lidar, or maybe by a radar, whatever that can sense the surrounding environment. And then the robot thinks for a little bit. There's a computer, do a little bit of thinking, and then lay out some action plan, do the stuff. A human, roughly, we also follow this pipeline, where whenever we want to do something, we first look around and we think about it a little bit, and then we do our action. However, mm, human can also think about things whenever we are actually doing the thing, right? For example, when I grab a water bottle or when I grab my iPhone, I don't first locate the water bottle and close my eye and grab it. And whenever I finish, I open my eye again. Uh, and whenever I grab it, my hand can feel this thing. My hand can feel that there's something in my hand and there's a certain shape to it. So I always have this sensation, always have this feeling. But most robots don't do this. And the reason is a little bit complicated. So to put it very simple, human, like even though we have made tremendous technology breakthrough throughout so many years, we still have very limited sensor technology. Traditionally, most robots are equipped with a so-called rest mount force torque sensor. That is this thing. So this thing, whenever the robot grabs something, it can tell you the force or torque uh, that the robot exert on these things, on this object that it manipulates. But here comes a very immediate question that is this thing is very far away from the actual place where things are going to be manipulated. So this distance creates an issue that is we have no contact geometry, we have no contact force, and we have no contact with the object in general. We are we are doing a very indirect measurement. Then you might ask, like, why don't we do a direct measurement? Like, are we stupid or something? And the reason is we actually don't have like sensor as good as human skin. Like human skins are very trivial, I would say, in our daily life. Like everybody has skins, and like it doesn't seem to sound like some magical thing. But if you think about it from a sensing perspective, it is a very awesome sensor that has very high resolution. Like I once read an article saying that if there is a surface that is completely flat and you put a slight object that has 6 nanometer dimension and let the human touch it, the human can sense that 6 nanometer object on a flat surface. That is although this is a bit maybe a bit of an urban myth, but that shows that like but in your daily experience, you definitely feel that we have a very high resolution when it comes to touching something. And we have we can sense temperature as well, right? Like when I grab a hot chocolate, a cup of hot chocolate, I can sense that it's hot. And to make things even more impressive, our human skins are very soft. So we can bend our finger like this without much issue. And we can grab things. When we grab things, the skins kind of wrap around the item. These are all very impressive property of the sensor that just like maybe just 5 years ago, we don't really have this in robotics community. We dreamed to have something like this, so we didn't. But that is like rapidly changing. So that brings us to the topic of tactile sensing, tactile perception. So we're seeing rapid progress in the tactile perception domain where we have this sensor. This one is called geosight. So it can sense when you put this, so on the right is a sort of a demonstration of what this looks like. So this is the Oreo, the cookie. And if you put it on the sensor on this image, this is a 3D reconstruction of this Oreo cookie. You can see that's very high resolution reconstruction of the cookie. Very small things, but very detailed representation. And this sensor is obviously a very big one, right? Like it's bigger than a human finger. But the same technology is the same as this small little thing. And if you put this on a robot gripper like this, you sort of imitating what human has in our hand. When we grab things, we have a sense of touch. Now you might ask like why this is important at all. What does it actually enable? So first thing is that this enable very um, delicate manipulation. So this is a Japanese company using this technology on gripping mushroom. So mushroom is a very soft food. You cannot if you use if you use a gripper with no this kind of sensing capability, you might very well like crush the soft mushroom. So they use a gripper that is very similar to what we previously seen. And by being able to see how much force you apply directly on the contact surface, you can adjust the force you actually apply, and making manipulating of these fragile items much easier. So this is already seen in commercialization. And this is also very good at manipulating deformable objects like cable. So for example, here, this is a same sensor that we showed previously. As you can see, like when we play with the sensor, we can play with this rope, with this cable. on the right, we see the sensor, like what it looks like in a sensor's perspective. And things are moving very directly. Like we can see this image already changing. And we can see the force of different force that the gripper is applying and how much friction we have. Now, let's go back a little bit to this setup where like most traditional robotic system are still using. Like if we still place the wrist sensor here, there's no way we can capture these very delicate changes of force and friction using this system. So this enables us to do a lot of things that we didn't thought was possible, like for example manipulating this mushroom, and maybe in the future we'll see more robot that can manipulate cables and deformable object like maybe clothes. And something tangential to this, although not entirely the same, is that previously I mentioned about medical robots where they can perform very delicate operation that human surgeon found difficult. There's one big caveat is that just before this year, before 2024, all those medical robots had no force feedback, meaning that if the surgeon is like moving, manipulating these little knob, little controller, just like your PlayStation controller, the underlying principle is exactly the same. When you're manipulating this, maybe doing a surgery on a human, and say like the little knife, this things, when it hits maybe some organ or some bones, let's just say, um, the human hand here will feel nothing. You can only see that on your screen, on your little monitor, that, okay, maybe this robot is colliding with something else. But the human doesn't actually feel it. There's no force feedback to this little controller. And that has been a problem for 20 something years. The company, the Intuitive Surgical, the maker of the Da Vinci robots, has been around more than 20 years, but their robot never had these capability of providing a little bit of a haptic, a little bit of a force feedback. And that is changing this year. In 2024, they they start to sell their DaVinci 5 system, where they finally come with force feedback. And that is not exactly the same as tactile perception, like not the exact same technology that enable what we saw when manipulating mushroom, but they're very related. And then I feel like these four that I briefly mentioned are some of the biggest, I would say, some of the biggest progress that we have seen that enables robot to move around better bipedal locomotion and enable them to work with humans alongside humans instead of replacing human, and then enable them to manipulate things that are we thought robot couldn't handle, like cable or dedicate food or whatnot. But at the same time, there are also a lot of hurdles going forward in the robotics domain. So one thing is these long horizon planning thing. So again, coming back to this very, very impressive Atlas, I would say doing some tricks here, right? So what is this, how do we actually achieve this pipeline? Well, Boston Dynamics didn't they never like explicitly say like publish their technical stack. Most people in the community agree that they follow a pipeline like this, where first they have a library of whatever behavior that sounds or like looks very cool, like these. And when they want to do something like this, some engineer will come together and chain them together. And when chained together, it's like a dance list, that dance move that you memorize, like when to execute what. And during when the robot is actually doing these things, there's some sensor on the robot that you do small optimization based on your sensor reading. But this part is everything else, like how the sequence are designed by engineers. So this part is there's some human in the loop. So this actually pose sort of a significant challenge. For example, if we want to have robot that can make coffee for us, like at some point, inevitably, the robot will make some mistakes, maybe spill the coffee or whatnot. So when that happens, what are the robots going to do? Like the robot need to have the capability to reason about these long horizon tasks, how to, even if it's only the same pipeline of chaining behavior templates, how do we chain them together? This capability is very important. Although fortunately, in the late 2022, there's GPT coming out. So you might ask, like, how are these related? So surprisingly, a lot of robotists are working on this type of GPT as a brain for robots. So this is some example from my own research where we asked GPT to decompose a task. For example, open a drawer. Like how can you open the drawer? And GPT can did a reasonably good job of you first need to be in front of the drawer, you need to grab the handle, and you need to pull them out along a certain trajectory. And then you need to terminate the grasping. You need to release the handle. And this pipeline is entirely come up by GPT. By I think they using there's some common sense in the model. And this might turns out to be a very, maybe not the only answer, but at least a very useful answer to this uh, long, like a problem that long trouble robotics in the entire world. And a lot of variant, some people call it like large vision language model. Some call it large vision language action model. Things get like more and more complicated in name. But the underlying idea is the same, that we use GPT-like models to do these kind of thinking that we believe only humans sort of possess. Another hurdle is computer vision, that is perception. So the current AI revolution, or like the hype, was kickstarted in 2011 by the success of the so-called AlexNet. It's devised by three people, and the first author, Alex himself, and the Ilya, which is the founder of OpenAI, and Geoffrey Hinton, which recently won the Nobel Prize, Physics Prize, for his work on computer vision. And basically, that was a program that can tell cats from dogs. That was very simple. And yes, so deep learning, the current AI was kickstarted by computer vision, but it's sort of hijacked, or the hive was sort of hijacked by language, the GPT-like models. But of course, computer vision can evolve as well. So later, earlier, like 2 years, like a little bit later than GPT, Meta, uh, the Facebook company, released this model called Segment Anything that is like the name, I guess, claim. It tried to segment anything on a picture. Like this is a picture of New York. It tried to segment the cloud, the building, and each building should have their own segmentation out of this picture. This is very impressive. And we would maybe not so naively, but we would think that this can help greatly in robotics, and it actually did. But it's still, like, while GPT can talk like a grown up, like a human, the current state of the art in computer vision still behaves like babies with no object permanence, the idea of object permanence. This is again an example from my own research. So there are a lot of cubes on the table, and each cube with a different color. Hopefully you can see them. And by different color, that means that the robot recognizes they are different cubes. And now we put them together. And one interesting thing you can see is that this blue cube, like notice how here, this cube used to be a this cube used to be a red cube, right? Like before this human proceed to put this blue one next to it. And the moment that they get in contact with each other, suddenly the segment anything model believes that the red cube is actually a part of the blue cube. So this is like, that means that the model has no idea of temporal continuity, and made this very silly mistake. Like, if this is a production environment, it could cause like very serious consequences. And there is some other examples similar to this. So, for example, in this video, there are even more stuff, right? Even more stuff. But the idea is the same, different color for different cube. Like here already, we see that this cube that was yellow contour, like the model lose track of it. And another thing is that here, see here, at the moment, this one is a purple block. When it's moving, there's a brief, like you can see here, as there's a brief moment that the model thinks this one is actually the a block with green contour. So we see this all these temporal issues. That means that the robot has not the robot, but the model has all kinds of difficulty when it comes to these tracking problem. This what turns out to be a very huge issue in robotics when robots walking around in the real world. And another major issue is like coming back to the humanoid that we talked about in the very beginning. Even though we all like very excited about robot that looks like a human, so like is there like do we believe that human is the ultimate form factor of living creature? Like the human is the perfect form of any living beings? I feel like that seems pretty unlikely. For example, like whenever we want a chill room that's not too hot, instead of like having a robot just wave the fan for you, ideally we will want a air conditioner that looks nothing like a human but can perform much better at this job, much more efficient when it comes to making the room not as a like hot hail. So this is another problem. Like, do we even need humanoid? Like when we spend so much money and R&D effort on it, and by extension, like, do we like those humanoid features like an arm or leg? Like, are they even necessary? Like, are we even need robots like in the first place? So this is a factory that handles salmon, and there are some animal dead bodies. So if you're not comfortable with these, please turn the head around for a little bit, right? So like when we see here, like how do we handle this salmon's body? There's no human arms involved except for those workers, right? Like there are some automatic like mechanism, machine design that can efficiently put them away. So do we even need these human features like an arm or legs to help us handle all these things? Um, I don't actually have an answer for this as well. Like there are a lot of debates within the community, whether it's industry or academia, that we're still learning. Like what is the ultimate form factor for robots? And one interesting thing I can introduce is that the state of art robot hand mostly has no pinky finger. Like they're only forefinger, and they will be able to handle most of the robotics manipulation job. This is manifested that maybe humanoid feature are not the most efficient, not the best thing to do, and there are a lot of room for improvement. And we'll come back to this later. But another major hurdle with robotics is that in general, automation is some of the most delicate problem in our society. For example, just a few weeks ago, there are a huge strike in the in a U.S. port, the handles offloading like the containers from ship that the U.S. import from other countries. And you might not know this, but US has some of the least automated ports globally. And by some efficiency ranking that some think tank and some researcher did, the US actually has the least efficient port in the entire world, not among developed countries, but the entire planet Earth, because people has this strong um, opposition to automation. And I do think they have very good reason to think of this way. So another Nobel winner this year, Darren, he thought that in his paper, he examined data that shows that automation is increasingly displacing jobs faster than creating new one. And but although like the implementation of automation is not exactly clear, for example, there are also economics believe that well, there are like automation enables company to grow beyond their potential and at the long term create more jobs. So, but as for now, we don't really know. So people have their doubts about robots and automation that prevents them from growing faster in our society. We can do a little quick case study on Amazon. So in, just a few years ago, Amazon has like a little over 200K robots. Just in these span of 4 to 5 years, it has grown to close to 1 million. And at the same time, Amazon has this 1.5 million human employee. So there are a lot of prediction that just within this decade, Amazon will have more robots employed than humans. So what kind of robots that Amazon actually utilize? So there are a lot of like different names, different models, but basically they come down to two form factor. One is a mobile robot, like it has a name, that basically just move things from point A to point B. There are also some induction robots. Induction means that just moving from stuff from conveyor belt to the mobile robot, moving stuff around. And this is called roving. And roving is a very good example that like why robotics is hard, even in warehouse where we have very confined environment. So first of all, like there's no uniform shape, like everything looks kind of different. Texture is different and color is different. And sometimes when Amazon is doing some promotion, a lot of this bag will be printed with advertisement, right? And so it looks very different. And they're all very clustered together. So only recent progress in AI and computer vision can enable the system like Robin to do this picking. And one very, very challenging task that we thought would be very trivial is this so-called stowing challenge. So by stowing, what it means is that just there's this shelf with item that pre-packaged, they didn't get packaged. They come with like the seller's original packaging. Before they got put into Amazon's own package, what you need to do is that you need to put those things inside of those shell. This seems like this is surprisingly easy for human. If you go to this video, the comments will say this is the easiest job, the easiest money you can earn from Amazon employee, these warehouse workers. Like this seems easy, but for robot, it is very difficult because every time you need to execute a different trajectory, your arm need to move differently, and sometimes you need to move other stuff a little bit to make space for the thing you're manipulating right now, and you need to have some spatial awareness of like where should I put this, how to move other stuff to make way for this, and this comes back to the form factor that we talked about previously, is that Amazon later on realized a simple gripper is not going to do the thing because there's so many stuff Amazon handle. Like Amazon is probably the uh, sort of like the data it has on different objects is almost like OpenAI has the internet scale of text data. Amazon probably have an internet scale of object data in the sense that you need to handle so many different things. So Amazon later on realized, okay, maybe this type of big clamp is actually better than a lot of traditional solution like a gripper or a suction cup. This comes back to the form factor we discussed that we are iterating on what form factor is actually better. And this, as you can see, looks nothing like a human feature. Another thing is computation, like how do you think about the space that you needed for putting those items inside of this stove. And they use some computational tools to understand where to put them and where to where to make more space for this for the item you're manipulating. And like the result I want to show is a very nifty things that they did towards the end of this. This is a robot that can do a little bit of a stoving. Something like this. So like they mimic what human did by pushing things. So the robot can now do this pushing and dropping. And this very simple thing took Amazon a few years, and they're still testing this system, testing this stoving system, and they haven't entirely put these things in the large scale deployment, despite they are having so many, almost 1 million robots in their warehouse. And coming back a little bit to this societal issue is that I encourage you to search the stowing robots a little bit and see in Amazon Reddit, Amazon warehouse worker Reddit, and see how they react to this robot like testing. Because some of the workers are asked to help the engineering team test this robot, and they have different thoughts. Some of them are in favor of it. Some of them like dislike it like strongly. So if you're interested, you can search this thing on Reddit and see how people react to this interesting small robot project that Amazon's doing. And with that, I think I conclude my talk today. And we have like a little bit over 10 minutes maybe. And if you have any questions, just feel free to ask. And thanks everybody for being here. I really appreciate your attention and time.
If anybody has any questions, you can either add them in the chat or you can unmute yourself and ask that way. And then in the meantime, I'm going to add 2 links to the chat. One is just the overall Student Learning Hub webpage on C2 Smarter's website.
Mhm.
And that's where you can find both all the information of previous learning hubs as well as upcoming that we've scheduled this semester. And then speaking of, our next course will be Online Optimization Meets Urban Transportation, which is Friday, November 8th at 1 p.m. And I'm going to add that registration link as well.
Mhm.
We did just get, Irving, a question in the chat, which is just, I'll just read it to you. I just wanted to ask about the tactile sensors. Why is the research in that field very less? Is it because of lack of people working on that topic?
Yes. So um currently for the last few years, there are actually like I would say exponential explosion of research on tactile sensor coming out of all the different universities around the world. I think the reason is that just like many research, it needs a little bit of a um, like a sort of a point, like a explosion point, like a like a dynamite needs a little bit of a fuse, right? The fuse for this tactile perception explosion is a research paper coming out of MIT in like 2017, I think. In that paper, they basically invent this type of very high resolution tactile sensor that is very soft and can put on the robot gripper. And when that came out, that caused the explosion of following up work. And before that, there isn't no such work. And you might ask, like, why isn't there such a thing? That's kind of a difficult question to answer because it's sort of a counterfactual question. And you might also ask, like, why before 2011 there is no deep learning explosion, there's no AI explosion. That's a little bit difficult to ask. But I could say is that after that paper in 2007, there is an explosion of this field, of a very rapid improvement.
Great. And then somebody else had raised their hand. I'm not sure if you still want to ask your question, if that was you.
Uh, Hi.
Oh, yeah. I think if you can turn your mic up a little bit, that might be helpful.
Thanks. Hi, Irving. Thanks for your presentation.
Mm-hmm.
So I have a question regarding the project I believe you have done with the like human demonstration using VLM for the block building
Yeah,
project. Um,
this one
so
or
the block building.
this one?
Yeah. So
Uh,
in fact, I have a similar project where I try to use this the vision language model to analyze the traffic instance videos, I mean, video clips.
mm-hmm.
So I think I followed a similar process where I decompose the task to several atomic um, tasks like object detection, tracking, or even pose estimation. And then I, uh, I send those intermediate results to a language model for reasoning. But
Mm-hmm.
one problem that I noticed is that, I mean, not a problem, but a question is in my mind is that um I feel like it's more like a forgive my wordings, like it's I feel like it's more like an engineering project because it's really hard for me to inject some like so-called academic contribution because I basically just using a couple of off-the-shelf
Mm-hmm.
models and then I build them up uh
Mm-hmm.
finish an finish an objective. Um
Mm-hmm.
so I just wondering, like, do you have any like thoughts regarding this line of research? Like,
Mm-hmm.
what's
Yeah.
the merit that we should bring up or to advocate such projects to the broad audience?
Yes, yes, I see your point. I also had some similar feeling where I found doing research with large vision model or large language model incredibly easy. Like you almost feel like you're doing nothing. Like you're doing something that a elementary school student will be able to do without contributing much. Which I think is on one hand, I think it's inevitable because if you're not involved with the engineering of the model itself, which you couldn't because a lot of them are closed source, and even
Mhm,
if they're open source, because the computation that required to engineer them are so big in an academia setting, it's difficult to do so. It's just like you just feel like you're not doing much, which I think is sort of inevitable. And on the other hand, I feel like the way to bring a little bit of agency to this type of research is that you can propose new ways to utilize these models, um, new ways
mhm,
like a framework to apply these model. And
mhm,
I believe, at least in robotics, a few of the work that I observed that did made to be a bit of a success at least in the robotics community are all kinds of work that employed large vision language model as a one component of their entire framework, and their contribution is not simply using this large vision language model, but instead a framework that can solve this problem. And
mhm.
I think that's their contribution. Because like you said, using this large vision language model is incredibly easy and requires very little, I would say, training. I think that's a
Yeah,
good thing. That makes things more accessible to most people.
yeah, I see. Mm. Thank you. Yeah, thanks.
Thank you for the question.
All right, and that's perfect timing because it's 2 o'clock on the dot, so we can
Hmm.
wrap up. Thank you so much, Irving, for your presentation,
Hmm.
and for everybody for attending and for your questions. And yeah, we hope to see you at the next one, which is again on November 8th at 1 p.m. Have a great rest of your day.
Right. Thank you so much. Thanks
Thanks.
everybody
Yeah.
for being
Thank
here.
you.
Thank you.